If you possess the exact blueprints to a house, you know exactly what the finished building will look like. For decades, science has applied this same logic to living things and thinking machines. The assumption that if we completely understand the starting code of a system, we can easily predict its final form. Biologists have long relied on this deterministic view. When they look at the genome, they see a precise instruction manual where specific genetic sequences and even individual mutations reliably dictate a living organism's development. Computer scientists approach artificial intelligence with a similar mindset. When building an artificial neural network, they write the initial architecture and the learning rules with absolute precision. The working theory is that controlling the math at the bottom level ensures control over the machine. But possessing the fundamental building blocks, whether they are strands of DNA or lines of algorithmic architecture, creates a false sense of security. We assume that writing the rules gives us total control over the future of a complex system. This assumption breaks down when we confront the physical scale of a living brain. The human genome contains a few gigabytes of data, but the brain contains trillions of neural connections. There simply is not enough room in our genetic code to explicitly map out every single wire. This image shows an early anatomical drawing of neural networks by Camillo Golgi. Faced with this complexity, scientists proposed the reticular theory. They argued the brain must exist as a fully connected web from the start, because building this from scratch seemed impossible. It took the work of neuroscientist Roger Sperry to prove that the brain does, in fact, develop from scratch. He demonstrated that early neural growth is guided by highly precise, deterministic genetic information unfolding over time, rather than random wiring. Meanwhile, early computer pioneers like Marvin Minsky looked at the exact same biological information problem and went the opposite route. Knowing they could never hand-code the vast number of specific connections required for a working intelligence, they bypassed the problem entirely and built their early artificial networks using completely random connections. This reveals a tension in both biology and computer science. Even when built on highly precise initial codes, they rapidly unfold into networks that operate in ways their original architects cannot fully predict. To understand why this happens, we have to strip away the messy variables of biological life and look at pure logic. Scientists use mathematical models called cellular automata to study how systems evolve without any interference from environmental randomness. This grid represents John Conway's game of life. It operates on a rigidly deterministic set of rules. A cell turns on or off based entirely on how many active neighbors it has. There is absolutely zero randomness in this math. Yet when those rules are set into motion, the simple shapes evolve into sprawling, chaotic geometries. After a few hundred iterations, the system produces incredibly complex structures that were never explicitly described by the initial on and off rules. Mathematicians describe these systems as undecidable. That means there is no analytical equation on Earth that allows you to calculate what the final pattern will look like based strictly on the starting rules. Because they are mathematically undecidable, there is no shortcut. The only possible way to know what the code will actually produce is to let the simulation run to the end. We scale this digital logic into physical space using L systems. These are algorithms that simulate the recursive growth of complex organisms using basic iterative loops. Consider this apple tree. Imagine it grows deterministically, where every single split, angle, and new branch is the direct result of the exact same predictable rule applying itself over and over again as the tree expands. If you try to accurately describe the final, fully grown tree with all its thousands of branches, the task is nearly impossible. But if you describe the short rules used to grow it, the task is trivial. Structural complexity is often an illusion of perspective. What looks like an intricately designed final form is actually just a handful of simple rules executed recursively over time. This same iterative reality applies to biological brains. The precise neural circuit of a butterfly is assembled through developmental loops that mirror those algorithmic rules. It is tempting to blame the unpredictability of these networks on the messiness of biology, a stray mutation, or an environmental shift. But the inability to predict how these networks will behave is an inherent property of the system itself. This is the defining feature of deterministic chaos. You can have a system that takes the exact same input and produces the exact same complex result with 100% probability, yet it will still function entirely unpredictably to an outside observer. A moment of wonder. Here lies the paradox of both natural and artificial minds. Having total control over a system's fundamental building blocks guarantees you absolutely zero control over how the higher-level system operates. This tangled mass of wiring reflects the reality artificial intelligence researchers face today. They feed massive amounts of raw data into their networks to train them, while admitting they have very little idea how the system actually stores or computes that information internally. The massive amount of information required to run a complex mind or a highly advanced AI does not actually live in the genetic code. It is not hidden in the starting architecture. That missing information is generated dynamically. It is created by the execution of that simple initial code as it iterates over time, building connections that the original architects never explicitly programmed. We have to abandon the idea that reading a blueprint allows us to foresee the future. The universe uses incredibly simple rules to build infinite complexity, and the only way to ever know the outcome is to let the simulation run.